Okay, so we are at another example problem time. And in the last video, I told you work on these 3 example problems, please, and try your answers and compare them to mine to see if they're going to be the same. And this question says, how can NMR distinguish the difference between the following 3 compounds? And we have just really lengthily discussed the whole concept of the number of chemical shifts, as well as how they split. And now we've thrown in things like doublet of doublets as well. Those are extra little things that we want to watch out for when they decide to happen, if they do happen. So A, B, and C, that's the name of the game with this example problem. And let's kind of use what we have learned already in all of these other examples to figure out basically how to answer these questions. All right, so here we go. So it looks like they all have something in common. They're starting off with this benzene ring. And then off of that benzene ring, this first one had like, I think, a NO2 up here at the top. And then down here, we have a bromine. Now, what they did not do is draw the other hydrogens that's on this particular chemical structure. And I'm going to do that just so that we don't forget them. So keep in mind that this circle is actually like a double, single, double, cause you trouble type of bond. And it really doesn't matter where they start, actually. It could be here, and then single, and then a double, and then a single, and then a double. But we'll just leave it like this for a minute. So what this means is that there's other bonds that's on these carbons that are not drawn. And I'm just going to go ahead and draw them. And each one will basically have one that comes off of here. And then that one, of course, is taken by the bromine. And then that one, of course, is taken by the NO2 or the nitro group. So the question is, how many shifts do we have? And then describe the multiplicity in them. And then if there is something like a double of doublets, which is something very specific now that we can look for, then we want to go ahead and mention that as well. So the first thing that we're going to do, like in all of the other examples, is guess what? Ding dong! We're going to go through and ding dong the molecule. All right. So this carbon with the NO2 group, that cannot generate a signal. There's no hydrogen that's there. And then this bromine, that cannot generate a signal. There's no hydrogen there either. However, this one can generate a signal. And that's because there's a proton there. And that's kind of our first carbon that we've got to so far. Ding dong! So there is a carbon with some protons, and those protons can generate a signal for us. Next one over, this is another carbon with a hydrogen, and guess what? That's another ding dong. So we get something there as well. And the reason is because it is different. So we're going to get a signal here. It's 2 away from the bromine, not 1 away from the bromine, and that is a different position. So that's not equivalent to our first ding dong that we did. All right, next up, we are now 3 away from the bromine, and that means ding dong. We can get something there as well. And then the next one is 1 and 2 away from the bromine. All right, so 1 and 2 away from the bromine. So position-wise, away from the bromine, those are both in the same, like ortho meta. Those are the meta positions of the ring. It's just meta one way and meta the other way in a way, right? Ortho, meta, and then ortho, meta. The problem, though, is that this is still a ding-dong type of carbon and proton, and the reason is because this one is next door to a nitro group, and this other position was not near a nitro group. So that nitro group does make them different, even though we can talk about doubling up on orthos and metas and paras and so forth, all right? So we do get 4 signals that's going to happen from this molecule. Now we want to talk about multiplicity that happens in the NMR, and we want to look at how these things are going to split, if they are going to split for us. All right, so I'm just going to not do an A, B, C, D. That's not really the purpose of this example problem. So I'm just going to do a 1, 2, 3, and 4. That's the way that we ordered them. That's the way that we identified them. And these are just random numbers that I'm going to put on them. It doesn't mean anything at all because the question doesn't want that. It just wants how many signals and what type of multiplicity. That is it. All right, so I'm going to start with carbon position number 1, and that proton, well, we're going to get a signal. All right, so Next door, we have a carbon with 1 proton on it. Okay, so what that means is that that is a 1 plus 1, which is a 2, and that means that that will be split, and it will be split into a doublet. So there will be 2 signals from position number 1. All right, so now let's move on to position number 2. And then here we have a different chemical shift. And then that chemical shift has 2 adjacent carbons, each one with a proton, doesn't it? Now, these are not equivalent protons, right? So that means we got 1 hydrogen here. So that's a 1 plus 1, which is going to be a 2. And then if I go right-handed side, that is another carbon with 1 hydrogen, and we add 1 onto that one, and that is a total of 2. And then we've got to figure out, what do we have, right? Is this a traditional type of 2 times 2, which is 4? And that is basically kind of the same train of thought that we've always done, and that's what we would do here as well. So at first glance, I would say, all right, this one's 2 and that one's 2. They are not equivalent to each other at all. And because they're not equivalent to each other, that's 2 times 2, which is 4, and that is a quartet. And I'm going to put a star beside of this one because I'm going to come back to that in just a second. But normally in the other example problems that we did, we would say it's a quartet and then we would move on. And that's what we're going to do right now, but we'll come back to it here in just a second. All right, carbon number 3 is here, and then the same thing would happen at this spot as well. We would go next door and we would see that carbon that has a hydrogen on it, and that is a different signal than the carbon that's down below once we visit that neighbor. So because of that, we would see a 1 plus 1, which is a 2, and then here we would see another 1 plus 1, which is a 2, because they are 2 different sets of signals here, right? They're 2 different shifts, and that means it's another 2 times 2, which is 4. So we have another quartet here as well. And then I'm going to put a star beside of that one, because now we know a special definition of a quartet, and that was this idea of a double of doublets. And we need to determine, are there double of doublets there, right? So this is what we saw in the last video, a double of doublets, and we talked about the differences here. So we'll come back to this in just a second. Okay, so number 4 finally is up here at the top, and then next door to that is a carbon, but there's no proton there that I have to count, and then next to that one is a hydrogen on that carbon, and that hydrogen on that carbon, of course, is going to be 1, so 1 plus 1 is going to be a 2. So that is another doublet that we're going to see here. So far, what we've determined is that there's 4 signals or 4 chemical shifts, 2 of which are doublets, and there's nothing special about those, but the other 2 are quartets. And I need to figure out, are they normal, traditional type of quartets now, or are they called double of doublets? So if I go back to the double of doublets definition, it says that it is a split from 2 non-equivalent adjacent protons. All right, so what does that actually mean? Well, if I look at this particular structure and I go back to position 2, which is where I want to start, that's kind of the first one that we saw. If I go up and I see a 2 here, and then if I go to the other side and I see a 2 there, that is giving us this quartet, right? So the definition of double of doublets basically means, all right, what we've got are 2 from one side and 2 from the other side, and they are not equivalent. And we've already determined that. They're different signals here. They are not equivalent to each other. So because of that definition, what we actually have here is a quartet, but in particular, we have a double of doublets here, because those 2s that are coming from either side, they are from different chemical shifts. So they play off of each other a little differently. And if we look at that chemical shift, what we would see are 4 splits, because we already said it's a quartet. But the difference here, the more specialized definition here, means that those splits will be about equal in height. So whenever I see this quartet that is at the same height all the way across, this is a very good sign that we're getting 2 on one side of the carbon and 2 on the other side of the carbon. And in particular, really what that means is that on to the left and to the right of that chemical shift, we see a carbon with 1 hydrogen and then a carbon with another 1 hydrogen. Both of those are going to be the same. So again, it gives me a little bit more information about a chemical structure if I can pick those up. All right. So now number 3 was also a quartet, right? So I just want to double check. Is this a traditional quartet? Is this something that we have basically seen and identified in the previous examples? And would that normal quartet look like this, where the first one to the left and the last one to the right are shorter than the ones in the middle? Or is this a more of a specialized quartet that's the double of doublets? So if I look at carbon number 3, and carbon number 3, of course, is right here. I'll look to the left and I'll look to the right. These are non-equivalent to each other because we got different chemical shifts on those, right? That's the first definition requirement. They are different chemical shifts. So here to the left and to the bottom, I've got a carbon with 1, that's a 2, and then I've got another carbon with a 1 hydrogen, which makes that one a 2 as well. So I get a 2 and a 2. So that's meaning like a doublet there, right? And they are non-equivalent. So I actually have another double of doublets here. That, again, is what that definition means. So it lets me know that this carbon is sandwiched between 2 carbons that only have 1 hydrogen apiece on them. I mean, that is what that's related to in this example, right? So once more, a little bit about chemical structure, just basically looking at the splitting and the way that that happens, and all of them are at the same height in the splitting on the NMR spectra, and I know that those carbons are not equivalent. And now I also know that those carbons are coming to me in forms of 2 and 2, which means 1 hydrogen on one side and 1 hydrogen on the other. All right, so this chemical structure, 4 chemical shifts, 2 of which are doublets, and 2 of which are double of doublets. That is the way that we would answer that question. All right, so now let's move on to B. And for B, we saw something very similar. We saw a ring system here in the middle, and we saw this alternating double, single, double all the way around. And we see an NO2 group just like what we had in A, and we also see a bromine just like we had in A, but they are separated now by 1 carbon. All right, so the basics of that problem are still there. There's nothing special here, and I'm going to look at this and I'm going to go, oh, you're not going to trick me. So there is a hydrogen here, and there's a hydrogen there, and there's a hydrogen here, and then there's going to be a hydrogen there. So we need to determine the number of chemical shifts. All right, so we're going to ding-dong the molecule, and when we do that, well, let's kind of take a look. I keep clicking on the slide instead of the actual draw pad. All right, so here we're going to ding dong. There's going to be a chemical shift because that proton is in between an NO2 and a Br, right? Okay, so if we move down and around like a clock, we'll work around like a clock. This is also going to be a ding dong because that one's next to a bromine, but it's not directly next to an NO2 group that has a carbon on it, right? So because of that, that is a different proton, and it's a different carbon, and it's a different chemical shift. And then we move on up, and that's going to be ding dong. So we're going to see another shift there as well. And again, it is different than the others because this is not near a bromine or an NO2 group. And then finally, as we work around to the 12 o'clock position, that's also going to be a ding dong because that is different than the other 3. That is now directly beside of an NO2 group and no bromine on the other side directly. So that is a different type of carbon and different types of protons as well. So just like with example A, we're going to see 4 signals that show up in this molecule, and we need to determine the splitting or multiplicity of these signals that's inside of this molecule that will show up on the NMR spectra. All right, so no big deal. still, we just do what we've always done. So if I begin to look at this structure and I begin to focus on each one of these protons, well, left, I don't have any protons at all. And then up above, I don't have any protons at all. So that means that this is going to be just that signal and that signal only. There's nothing on either side of that carbon as far as kids and children go. So this is going to be a singlet, and that's something that we did not see in the structure for A. So this is going to help me kind of match different NMR spectra to different molecules. So this is a singlet, and we didn't have that in A at all. All right, so as we work on around, let's go to this one now. And if we look at this proton, that's on a carbon. Well, to the right-hand side of that, there's no proton, so I don't count it. And up above, I see a carbon with 1 proton. So this is going to be 1 proton plus 1, and that's a 2. So that means this thing is going to be a doublet. All right, so that's easy enough. Then we go up to the very top. I want to do the 12 o'clock position next because that's always going to be a little bit easier. And the reason is because there's something next door that doesn't have a proton. So I'll only have to worry about one of these. So as I go left, I see that same funny little proton that's out there. It's just 1, so 1 plus 1 is 2, and that means that this is also going to be a doublet. So it will split into 2 separate signals based on the neighbor. So now we've got that 1 carbon that's left, and this 1 carbon that we're focused on is right here. And then down below, we see a carbon with a hydrogen, and then up above, we see a carbon with a hydrogen. So it looks like they both are CHs, but we've already identified that they are different chemical signals. They are not equivalent to each other. So basically what that means is that I treat them separately, one at a time, right? So down below, this is 1 hydrogen plus 1 is a 2. And then here to the top right-hand side, that is 1 hydrogen. So 1 plus 1 is another 2. So it looks like this one is going to be a 2 times 2, which is 4, and that is a quartet. Now, there is a special version of that quartet, like we've talked about in example A, where if I see 4 signals, there's a possibility that this might be a special type of one where all 4 will be the same height. And that, once more, is called a doublet of doublets. And the only way that this happens is that if those hydrogens that make that quartet, if they are non-equivalent, that is what we are after. So if we look at this example problem, just like we did with A, this is a different signal. That one at the top is a different signal. So therefore, they are non-equivalent. And that means that, yes, this is a double of doublets that we have here. So I need to be very specific in some of the terminology that we will begin to be using in the NMR interpretation. So, as with example A, this molecule will give me 4 chemical shifts. One of those shifts will be a singlet, and then 2 of those shifts will be doublets, and then a 4th of that shift, or the last of those shifts, will be a quartet, but more specifically, it will be a double of doublets, meaning that this one will give me those 4 splits that will be about the same height. So in my head, I know that the structure for that molecule at that position will have a CH on one side and a CH on the other, and they are chemically different from each other, meaning there's something else in the molecule that's making it different. A bromine, an NO2 group, an OH group, something on that molecule is making it different for those 2 CHs, which are otherwise the same, CH and CH. They are different. Chemical shifts are different, which means something else is on the molecule on that kind of electronegativity scale that's pulling on one side and not so much on the other, and they are chemically different because of that. All right, so now let's take a look at our last one, and that's C, and this is another ring system, and it looks like they did a double, and well, here, let me make it match that example problem just so that we're kind of starting on the same foot. So the double was here, single, double, and then off of this was an NO2 group, and and then on the other side, which is the para position, is the BR group. So we want to do the same thing here. We want to talk about chemical shifts. We want to talk about splitting. So I think that you can do this. I hope after all of these example problems that we did, I'm going to ding dong that one, and that is the ortho position. But look at this. If I go up to that one, that is also the ortho position. So I cannot ding dong that one, right? These two are exactly the same. And the reason is because both of these are next door to an NO2 group, and then they are 2 carbons away from that bromine group. We now have a very symmetrical molecule, don't we? Look at this. I can draw a dotted line all the way through the center and almost fold it in on top of each other. So we have a plane of symmetry here. So because of that, these orthos are going to be the same equivalent shifts. All right, so I can only ding dong once, and I'm going to ding dong this one. All right, and then we move on to the next one, and then when I do that, I can ding dong that one because this is 2 away from the nitro group and 1 away from the bromine group, and that does make it different than the first ding dong that I did. So this, though, is the same as that position. Plane of symmetries there. They're actually a perfect match. They are chemically equivalent. So here I can actually do another ding dong and have 2 signals in total. And that's basically why C is so different, because there's only 2 chemical shifts that are here. There's only 2 signals that I'm going to be getting from this thing, and that is it. Unlike A and B, which all were the same nitrogens, the same number of oxygens, the same number of carbons, the same number of hydrogens. They're all still a ring. It's just how those 2 groups were positioned to each other. We had an ortho, we had a meta, and we had a para attachment on these benzene rings. So here for C, the para position will give me 2 signals, unlike A and B, which gave me 4. And then each one of these, just to kind of follow through, each one of these will have a hydrogen on it, right? We know that they're there. I'm going to draw them, and we're going to see what begins to happen here. So if I take a look at this particular carbon with that hydrogen, I need to go and I need to take a look at surrounding neighbors. So I go next door and I see that carbon have 1 hydrogen. So 1 plus 1 is going to be a 2. So that means that this particular thing is going to be a doublet. I don't count the other side. And the reason I don't count the other side is because that particular one has no proton that's adjacent or next door to that. So I don't count it. I just ignore it. All right. So then we move on and we go to the next carbon that I would get the signal from. And that next carbon, well, I do the same thing. I would go to the right-hand side and say, how many kids you got? And they say, I've got 1 miserable kid and 1 miserable parent. So 1 plus 1 is 2. So this is also going to be a doublet. Now, I don't take into consideration the other side of the molecule. And the reason is because they are equivalent. And remember what we said, equivalent signals do not split each other. So I've taken care of one, and I do not have to take care of the other one. That is as simple as NMR is going to show. So I'm going to see 2 signals here, and each one of these will actually be just a full-blown doublet. That's what it's going to be. So yet again, drastically different than example A and example B. So that's how we've answered that example problem. And I don't think there's any surprises there, but I think that it's getting you more comfortable with this idea of what a doublet of doublet is. All right. All right. So now let's take a look at another example. And it says question number 24. All right. So question number 24 says, how would the NMR for the 4 compounds with molecular formula C3H6Br2 differ? All right, so this one's a doozy, right? I mean, if I take a look at this thing, for goodness gracious, there's 4 compounds with this particular molecular structure, C3H6 and Br. How can we actually draw these structures? That's what this example problem is going to be about. So I'll only have 3 carbons, which is there. And if I only have 3 carbons, you know, my mind is not really directly going to go to ring systems, because ring systems are typically 5s and 6s, not 3s. And I only have 3 carbons here. And then they tell me 6 hydrogens and 2 bromines. All right, so let's just kind of keep it simple. Let's try 1, 2, 3, and then 4, and then 5, and then 6. And then I do have 2 spots that are open, and those 2 spots could maybe hold those 2 bromines that would be there. So there is one possibility here that we've got for problem number 24. So I would need to describe the NMR of that structure if we analyzed it in one of those instruments. You know, what would that thing look like? How many shifts, and then how many splits, or the multiplicity is of each shift that we happen. All right. So next up, there's a different way that these things can come together. So instead of the bromine basically on both of this both of these bromines on that carbon at the end, I could see one on the end and maybe one in the middle. Okay, so that would be another option for me. I would still have the same number of hydrogens, same number of spaces that are available to me. That's not a problem. And then if I do it again, I'm going to see this 3-carbon chain, maybe 1 bromine on this side and maybe 1 bromine on that side. So there's a possibility for me. And then I would see 2 and then 4 and then 6 hydrogens, 2 evenly on each carbon. And then I get this, it says 4 compounds, right? So you might say, all right, well, fine. What I would do now is take these 3 carbons, and then if I put 1 bromine here on the end, and then 1 bromine there in the middle, and then I shifted it to there, what if I just put 2 bromines on the left-hand side? That would be my 4th one, right? Wrong. No, that's not what it is, because this would actually be the same as that molecule there. It's just the 2 bromines would be here over on the left-hand side and not the right-hand side. So this is actually not the 4th structure that they are talking about. So we've got to kind of figure out another way that we could get a different structure yet again from the same setup. So what I could do possibly is put both of the bromines on the middle carbon and not on the end carbon. So we would see both bromines on the end and then both bromines on the middle, and then we would see the bromines split here next door to each other and then here on either end of the molecule. So that will get you started with that example problem. So now that we've got these 4 structures, it's going to say explain the differences between the shifts and explain the differences between the splitting. How could we actually determine which one's which? So I'll let you pick up this example problem from there. So work on this one, see if you can figure it out, hit play on the next video, and see if you're going to get the right answer. I hope that you do, because this is the same stuff that we've talked about over and 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 over. So practice makes perfect, or at least it makes us better. And this is just another example problem that uses the same old hash that we've been given out ever since the very first lecture video. So good luck. Take a stab at them, hit the play button on the next video, and see if you've answered it correctly.